Good morning. This is the final lecture, and I re-recorded this lecture in 2021. Um, this will not be a lecture on theory, but it will be an exercise integrating a lot of the concepts we've seen in the lecture. The students for biological control systems may do this in the beginning of the afternoon, depending on how much time they needed. I set up this exercise last year with Berend Westerhoff and Marijn Mulder, and they at least Marijn may be using some of this later classes. So let me introduce the exercise. We're going to work you are going to work toward a mathematical model in state variable form of what's called a three-element Windkessel representation of the arterial circulation. I will explain what that is. So in the comment section of this video, there's a link to a Wikipedia article on the Windkessel model and where that came from. That's about a century-old model of the arterial tree. At the bottom you can see the ventricle and then the arterial circulation and later on the venous circulation. And there was an analogy with a fire hose. There's on top there is a reservoir and then a pump, which is certainly at the time it was a pulsatile pump like the heart, and then the water got into this Windkessel where it accumulated, and on top of that there's a pressure depending on how much volume there is in the Windkessel, and then this pulsatile flow of water goes through the hose that the fireman holds, and there's a resistance there, and it comes out as an almost continuous stream. And this is very much like our circulatory system. What I'll do is I'll follow to model this first conceptually, and then I'll let you do the mathematical model. I'll follow our procedure for modeling and simulation. So the requirement in this case is fairly simple. We want a model for the relationship between the flow rate that goes into the Windkessel, the arterial system, and then the pressure in the Windkessel itself. Now, the article, Wikipedia article, and lots of people use an electric analog like in the bottom, but as I explained before, I prefer to use direct hydraulic representations. So that's the top diagram. We have the flow, and that's a symbol for a pump, a hydraulic pump, flow rate, Ft, resulting in a pressure, a back pressure against that flow rate, flowing through a resistance, is what's called a central resistance, RC, and then ends up in the reservoir with a Windkessel compliance CW. And the two variables that characterize what goes on in that Windkessel are the blood volume, I'll talk about the circulatory system, and the blood pressure, P W for the blood pressure and VW for the volume in there. Then there is the outstream of the Windkessel, and that goes through a peripheral resistance, which corresponds and then ends up in terms of the circulation on the venous side. The difference between the flow into the Windkessel and the flow through the peripheral resistance is the volume that accumulates or gets returned in the Windkessel itself. So my question to you is to derive a mathematical model in the form of a state variable model, and So I'm asking you to derive two equations. One is for the change of the volume in the Windkessel over time. We could have chosen another state variable, pressure, but I choose volume here. And then write an output equation for the pressure in the Windkessel. You're going to use this table, which I've had an occasion to introduce. And this is a bit of an awkward table, but it's a crucial table in the modeling and simulation process because it allows you to make the link between the conceptual models, the symbols, and then the mathematical model, so the mathematical model equation. And we're mainly going to use the symbols for the resistance, Ohm's law, and for the compliance. And we're going to ignore the unstressed volume. And what you can, I'm not going to introduce Ohm's law again, but for the compliance, what we see if we put that unstressed volume to 0 is that when the volume increases, the pressure increases, and vice versa. If pressure increases, the volume increases. Think about a balloon that when you blow it up, both volume and pressure rise, and in this case we represent this via a linear increase. So here we have all the material to do this exercise. So try to derive this state variable mathematical model of this 3-element Windkessel with as an input variable flow of T, a state variable, the volume, I already mentioned that, and then the output variable PW of T. I'm now going to present the solution in this video, so you may want to stop your video now and try to do it yourself first. You'll get a much more interesting learning experience out of that. So what we do is, well, I mentioned the state variable selection, but that makes an important point, that the state variables are not unique. We could have derived a model writing it in terms of the pressure PW, for example. But we picked volume, and one of the reasons I picked volume is that there is a law, conservation of volume, and the change of volume in this compliance is equal to the inflow, which is equal to F of T, minus the outflow, which is the flow through the peripheral resistance Rp. Now that equation already gives us the change of volume as a function of an input variable, which is what we want, but then we have that Fp still there. And that's not either a state variable or input variable. So how can we get a bit closer to our target there? Well, first of all, we can observe that the flow through Rp is the pressure over the resistance. And that's, again, I'm applying Ohm's law. So Fp, I can replace that by Pw divided by Rp. Still doesn't quite get me there because I would have that Pw there, but I can replace Pw also by the compliance characteristic, which is volume Vw over compliance. And if I make those two, if I substitute the compliance equation into the resistance equation and then back to the top, I can write the state equation, and I can write the change of time of volume is equal to the flow minus Vw divided by Rc, and that is what I'm looking for. It's in how does volume evolve as a function of itself and as a function of the input variable F of T. So I'm done as far as the state equation is concerned. And then I said that I was interested in the output equation, and the good news there is that we don't have to derive anything new because it's actually, we already have that a little bit to the left of it. That output equation is simply the pressure as a function of volume. Volume is a state variable, and the flow rate doesn't play a direct role here. So we're done deriving the mathematical model in state variable form for this Windkessel. So that wasn't so hard. And let me know if you have questions, and then we can discuss this. To elaborate a little bit on this, and this is no longer part of the exercise, let us assume we're interested in this pressure P of T, which is the pressure against which the pump works. So that's an important pressure, certainly, and not only for firemen, but also for our heart. We get this back pressure, and if we're in hypertension, our heart has to work really hard. So how can we derive an equation for that? Well, and we consider that an output equation. It comes out of the system, a dependent variable of the system. Well, that's quite easy, as you'll see. The pressure P of T is equal to, and I'm looking at a downstream pressure PW of T plus the flow rate through that resistance times the resistance, the RC, the central resistance. And that's, again, if you look at it carefully, an application of Ohm's law. And then if I want to write that as in terms of state variables and input variables, I have to replace the PW by VW divided by C, which is the compliance description. And at the bottom, I get a new output equation. And this output equation depends both on the state variable and the input variable. And the RC shows up. Until now, we haven't used the resistance R of C. So I have a second output equation here for P of T. So now that we have this mathematical model, we would like to implement it in code, in software. So how do we do the software implementation? And I kept the state equation and the first output equation in blue on the right of my screen. And we're going to use, the computer cannot do continuous time. The computer has to work, a digital computer has to work with discrete time. So we're going to divide up the time in discrete steps. T is continuous, but N is equal to 0, 1, 2, 3, 4. And T is what we call the integration step size. And then we can use the most simple method to discretize a continuous time equation is a Euler method, and there's a forward and a backward version. I use the forward one. I can approach this derivative by two values of volume, a step T apart. So and we write that as VW of n plus 1 minus VW of n. Be a bit careful here. It means that you substitute T in the VW equation by n times big T. But the notation is a bit simplified by n plus 1 and n. So this is an approximation of the derivative. And if we fill that approximation in the formula and we replace T continuous time by n, we get the discrete time state equation. So what I did is I put this formula for the derivative in the continuous time equation, and then isolated the VW of n plus 1. And that's why you get this multiplication by the integration step size on the right hand side. So the equation, the discrete time state equation, is a bit more complicated than the continuous time equation, but it does look very similar. And what we have there is that if at a given time n, I have my volume, I have my flow rate, and I can now make a prediction for time n plus 1. And that's usually a very small step in time, but if we repeat that process, we integrate our equation, and we can simulate over much longer times. The discrete time output equation is identical to the continuous time equation, other than that we replace continuous time by discrete time. When we do this, we do have to carefully select the integration step size. And because if we make it too large, we'll make big steps, but our approximation of the derivative will not be very good. So our signal will not follow, not track the continuous time signal. Our simulation will be very fast, but it won't be very good. If we choose our t too small, if we make large T, uppercase T, too small, then our calculations are going to take a long time because we make very small steps. For example, if we think about cardiovascular phenomena that take place in seconds and milliseconds, if we take an integration step size of microseconds, then our simulation is going to last a very long time. And so there's a balance there between what is not too large, not too small, and a good value is about 1/10 or 1/20th of the main system time constant. In this case, it's the multiplication of the peripheral resistance and the Windkessel compliance. There's another a bit more subtle consideration. If the integration step size gets really small, the increments may become so small that they get lost in the truncation errors. So there's another danger of having too small an integration step size. So choose this carefully, but you can verify this experimentally and see if it works well. Of course, this is true. What I'm saying is true for most simulation languages. When you use Simulink, a lot of this is transparent, so be a bit careful about that. Simulink does this for you, but it doesn't make this explicit. So sometimes you can get mistakes that stay a bit hidden. Final step is the simulation, and I'll just give you an indication for that. So what we need for the simulation is the input signal, and we need parameter values. And for the input signal, if we want to use a simple input signal, we can create cardiac ejection and give it this form, a triangular pulse, in this case every second, so a heartbeat of 60 beats per minute. A good value would be 300 milliseconds or 0.3 seconds for the pulse duration. And each pulse, the surface area of each pulse should be around 83 milliliters, which if you calculate this over a minute, and it gives you about 5 liters per minute of cardiac output. So that would be an adult value. And the initial volume of the Windkessel can be set to 0. I won't do this because the actual simulation is not part of this exercise, but it will be part of the biological control systems class. But you have to run the simulations, we have to give numerical values to the parameters. Be careful about the units. Time unit should be seconds, volume unit should be milliliters to be consistent, and the pressure unit is to be determined. And once you have these values, you can implement this in code and run it. So that takes us to the end of this introduction of modeling, and I had fun preparing this class. I hope you'll enjoy. I hope you enjoyed listening to and doing this exercise, and I hope you will enjoy the rest of biological control systems. Take care. Thank you.